Hello, this is Mr. Huff, and let's see if we can get through this. Let's look at an example of a system where we have two masses on this bar at the top that has a radius r. So we have mass here, we have a mass here, okay? We have a tension applied here. This is a small radius here. So we can see the rope is like the little string here is wrapped around this column in the center. And as you follow this string across, is connected to a mass that has 3 times the mass of the masses at the top. So that's the scenario we're looking at. The first thing we should consider is the sum of the forces. So we're looking at the net force of the system is going to be equal to mass times acceleration. And we know that the 3 times the mass weight is pulling down. So there's that force. And opposing that is tension, and that is equal to mass times acceleration. So we can rearrange this to solve for tension by saying tension is equal to, by adding tension to both sides, I'm subtracting MA from both sides. So we end up with this formula. Okay, so that's the first thing we know. Another thing we know is that if we look at the rotational inertia of the element at the top, that's going to be the sum of the masses times the radius squared. So if we look at that, we're going to say that's equal to mass r squared, the big R, plus mass r squared, which is equal to 2mr squared. And that is our rotational inertia. Another thing we need to think about is the sum of the torques. The sum of the torques is equal to rotational inertia times the angular acceleration. The torque in this case is coming from the tension and the radius, and that's going to be equal to this. So we can rearrange this to solve for the tension. Tension equals rotational inertia times the angular acceleration divided by r. So we can go plug this back into our formula that we had before. Rotational inertia times alpha over r equals 3mg minus ma. So far so good. Another equation we need to keep in mind is the Fisher equation that we talked about earlier this year. This is one you would need to commit to memory. So we have the tangential acceleration is equal to fishy thing times r. So that means that the fishy thing, alpha, is equal to the linear acceleration divided by the radius. So we can go replace that in our equation. So now we have a over r squared equals 3mg minus ma. The next thing we can do is think about this rotational inertia. We previously said that that was going to be equal to 2mr squared, and then we replace I in our previous equation, equals 3mg minus ma. That's an A. I'll do that last one, A. Okay. When we look at this equation, we can go in and get rid of a couple of things. Well, actually, we can just get rid of one thing in this instance. I can factor out this m, and this m. And that brings us to this equation. So we have 2r squared a over little r squared equals 3g minus a. If we want to solve for a, we have to get a all on one side, but the problem is we have a denominator over here, the r squared, so we need to multiply both sides by r squared so we can use addition to get the a's together and then solve for acceleration. So we're going to multiply both sides by r squared. That gives us 2mr squared a equals 3g little r squared minus a r squared. So now we can start solving for a. So we have 2mr. Actually, the m doesn't belong, does it? Sorry. My bad. Cross that out. It's 2ra squared. Actually, squared right there. Okay. Equals 3gr squared minus ar squared. It's really important to pay attention to what you're doing when you're doing these lengthy algebra things. Okay. We're going to move ar squared to the other side. 2r squared a plus ar squared equals 3gr squared. And if we look at this, we can factor out the a's. So we end up with a 2r squared plus r squared equals 3gr squared. Okay? So now we can divide both sides by 2r squared plus r squared. And that gives us our final formula here. So let me change to a celebratory color. We'll make it a nice red one. So our final formula is going to be acceleration is 3gr squared over 2r squared plus r squared. And that's your final formula. In the problem that you see this on, just show your work all the way through, get as far as you can, and you'll be okay.